Okay, we're back with the videos. This is section 8.2, arithmetic sequences. So first we're going to look at these four sequences to talk about what is an arithmetic sequence. And I'm saying arithmetic and not arithmetic. You pronounce it arithmetic when it's an adjective. It's describing what kind of a sequence we have here. So let's look at the similarities among these sequences, and we're going to find out, just like on Sesame Street, one of these things is not like the other. If you take a moment and look at each of these sequences, we might notice that with this sequence, to get from 10 to 8, I would add a negative 2. If I keep repeating that, I'll get the next sequence, or the next term. Add a negative 2, add a negative 2, add a negative 2. And it gets us all the way through these 5 terms. Let's look at this one. If I take from negative 24 to negative 16, if I add an 8, then that gets me from negative 24 to negative 16. Add another 8, and I get to negative 8. Add another 8, I get to 0. Add another 8, I get to 8. Take a look here. Take 4 and add 5, you get to 9. Add 5 to 14. Add 5, add 5. This one, you can't do that. There's no number that I can add the same number every time to get to the next term. I could add a third between a third and 2/3, but if I try to add a third between 2/3 and 4/3, it won't work. If I add a third to 2/3, I'll just get 3/3, not 4/3. The pattern is that, this is doubling each time, and that's a valid pattern. It's just not an arithmetic pattern. It's not an arithmetic sequence. Okay, so that was our first concern. What is an arithmetic sequence? And an arithmetic sequence is one where you add the same number every time. And that number that you add every time to get from term to term, to leapfrog like that, is called the common difference, and we call it D. The common difference. Now, in each of these, how would you find the common difference? And keep in mind, this is the number that you add to get to the next term. So, while this is very straightforward, what's the common difference? What number do I add? I add a 5, add a 5, add a 5. What do I add here? Add an 8. And here you might say 2, because, yeah, there's 2 between 10 and 8, but you add a negative 2, okay? So, in general, how are we going to get from, or how are we going to find the common difference? If we come to this guy right here, we could take 9 and subtract 4. We could also take 24 and subtract 19. For this one, we could take negative 8 and subtract negative 16. So in general, if we have a sequence that is a sub 1, comma a sub 2, comma all the way up to a sub n minus 1 and a sub n, wherever you are in the sequence, if you're at some arbitrary a sub n, if you want to find the common difference, you could just subtract the thing that came before it, a sub n minus 1. Okay? So that's how we find the common difference. You just take a term and subtract the term before that term. That's going to give us the common difference. If you wanted to test to see if a sequence is arithmetic, you could just take any of these terms and subtract the one before it, find that number, it will be a number, but then go to the next term, next pair of terms, and do that subtraction again and see if it works out. See if that subtraction works for every pairing. Okay? Now we're going to figure out, is there a formula for finding the nth term of an arithmetic sequence? With its general structure of you add something every time, can we maybe make a formula that would tell us, we'll take these things and put them in the formula, and then you'll have the a sub n rule, the thing that tells you how to find an arbitrary term in the sequence. Well, let's look at this sequence right here. 10, 8, 6, 4, 2. Okay. What's common among these? Well, I know that I'm subtracting 2, so maybe I'm going to subtract 2 is going to be part of my rule. Let's see, maybe, I'm subtracting 2 each time, at maybe the number of times of the term that I'm on, so maybe it's minus 2n. Well, if I'm going to subtract 2n, then let's make sure that I'm going to get 10 when I want the first term. That means this is a sub 1. This is a sub 1. I want to be able to plug in a 1 into n and get negative, or not negative, but positive 10. So I put in a 1, so that makes this negative 2, subtracting 2. What would I have to subtract 2 from in order to get 10? Well, I'd have to subtract it from 12. Okay, so in general, the formula here for the nth term of an arithmetic sequence would be that a sub n is equal to a sub 0. Remember, this is most often a sub 1 and a sub 2 and a sub 3 and so on. So this guy back here would be a sub 0. For this sequence, a sub 0 was 12. That was the number that I needed to subtract 2 from in order to get 10. So then I'm going to add the common difference times n. Okay? And this is how our book in our class does this. This is the formula they use. So here is another formula. Okay? Lastly, let's take that first sequence again. 10, 8, 6, 4, and 2. Okay. Now, I'd like to, as much as I can, kind of derive any equations we're going to use, and I've tried to do that here. And now, we're going to try and do it again. The thing that we want to do, and then after that find a formula for, is add up all of the terms in this sequence. We want to find the total when we add them all up. Well, we could look and see, well, this is 8 and 2 is 10, and 6 and 4 is 10, so that's 10 and 20, and there's a 10 again, so that's 30. So we can see what it is. But what if this was, 50 terms? We don't want to look at them and add them all up individually. It'd be nice to have a formula. And you might think, maybe there is a formula for all arithmetic sequences. You take something about maybe the first term and the common difference, and throw it all in a bucket, and out comes the sum. So let's see if we can figure that out. The thing that I'm going to use to figure this out, or to display the formula and kind of a mini proof, is a picture. I'm going to draw this picture of dots, which represent the sequence. There's 10 dots, and next I'll draw 8 dots. And next we'll go with 6 dots, 4, and 2. Okay, these are all the terms. All of these dots represent the total number, the sum of all of these terms. And they don't look that easy to count as dots right now. But what I'm going to do is I'm going to take all of these dots, this picture right here, I'm going to copy and paste it and then flip it over like another set of stairs that sits perfectly on top of this set of stairs, if you imagine these as stairs like this. Okay, so it's going to get flipped over and put on top, and we'll see what that's going to look like. Here's our 8 dots. I guess that was 6. Oh, we should have been going a little further, because these 2 dots are going to wind up on top of those 10 dots. Okay, so here I have 2 dots, 4 dots, 6 dots, 8 dots, and 10 dots. Exactly the same picture as I have right there. I hope those colors are showing up. Now, how can I count all of these dots in this rectangle? Now, we've made it a rectangle. That's the convenient part of it. When I make it a rectangle, how am I going to count all those dots? Well, all I have to do is add up these dots and multiply it by these dots. Okay, well, what are these dots? We know this is 10, because that's our first term. And these here are 2, and this side is 5. So if we take 10 and we add it to 2, multiply it by 5. Now, we did find all of these dots, but the problem with that is we weren't looking for all of these dots to start with. We were only looking for the black dots. By multiplying 12 by 5, we've counted too many dots. But how much too many dots have we counted? we've counted the black dots, and then an exact copy of the black dots, the red dots. So we have twice as many as we want. So if we divide this number that we found in the rectangle, if we divide that by 2, then we'll have the correct number. And let's see what happens here. We get 12 times 5 over 2. You cancel the 2 and the 12. This becomes a 6. 6 times 5 is 30. So there we go. So maybe we can pull a formula out of this. Let's call this formula the sum formula. Let's call it the sum of the first n terms. Okay, that's how this is commonly written, S sub n. So let's try and take these specific examples from this problem and then extrapolate them into a general solution, a general formula. Well, and this is pretty convincing that it'll work every time. I've got this common difference, I've got this stair-stepping action. I'm going to be able to make this copy, set it on top of the original every time. I'm going to be able to construct this rectangle every time. So to construct this rectangle, what makes up this side? Well, this is the first term, and this is the last term. Okay, so I had written the first, or put the dots of the first term first, and then on top of it comes the last term. So that would be the first term plus the last term. What's the last term? Well, there's n terms, so the last term would be a sub n. I'm going to multiply it by 5. What did 5 turn out to be? Well, let's see. This is my first term, my second term, third term, fourth term, fifth term. So the 5 was the number of terms that I have in my sequence, in my finite sequence. So that would just be n. N is the number of terms. And then divided by 2. 2 is a constant here. 2 was because we had counted twice, or 2 times too much. 2 times of what we wanted to count. So we divide the whole thing by 2, and we're golden. This is our formula for the sum of the first n terms. Okay. It could also be written as, S sub n could also be expressed in sigma notation, I equals 1 to n, of the formula for an arithmetic sequence, which was a sub 0 plus d times n, the common difference, times the term that you're on. Okay? And actually, since we're using this notation, this shouldn't be n, it should be I, but it's the same. It's just that variable that we keep changing as we progress through the terms. Okay? So those are some general ideas of arithmetic sequences. We'll do some example problems here in a minute.